We are going to talk about electronegativity. That's where we're starting out today. So you should find this section in your notes. All right, there we go. Now I can move around on here and talk and everything. All right, so electronegativity is a measure of an atom to attract electrons. So certain elements on your periodic table, do I have a periodic table on here? No. Certain elements on your periodic table will want to gain electrons to become more stable. In what condition do atoms become stable, or ions become stable? Atoms. What do they want to look like?
Oh, the
noble gases. Okay. So there's a couple ways that they can fill these electron levels and get these noble gas configurations like noble gases. They can share. We will talk about that when we get into a future unit. Right now, we're concerned with transferring. Now, your non-metals are going to gain electrons because it's going to be easier for them to gain 1, 2, or 3 electrons to look like the noble gas. Does that make sense? So if they gain electrons, then they're going to fill that electron level. Does that make sense? Okay. Now, the element that wants to gain electrons the most is fluorine, because it is closer to the nucleus, okay, and it just needs that 1 extra electron and it'll be there. It wants that more than chlorine does, because the chlorine, that outer level, is further away from the nucleus. And as we move down, you're getting further away from that effective nuclear charge. Does that make sense? All right. And this just needs 1, so it wants it more than like oxygen. It wants it more than nitrogen. Okay? Now, that is your nonmetals. If you are a metal, though, so let's take potassium. How far away is it from being a noble gas? Think about it, though.
If we were trying to gain an electron, that would be a lost cause. But if we were to lose 1 electron, then...
Exactly. Gaining all those electrons would be difficult. So I think that's where you were at. You were trying to get it to gain a whole bunch of electrons to get over to here, right? But as Ray said, if this guy loses 1 electron, then what does it look like?
A noble gas.
Yeah.
That's what.
Okay. So it's beneficial for them to lose electrons.
I'm sorry, but can you repeat the question?
Yeah. So if it loses an electron, does it want to gain electrons?
No.
It wants to lose them. So its electronegativity is going to, remember the definition of electronegativity, right?
No.
Okay, well, let's flip back over to this slide and see what it is. It's the ability of an atom to attract electrons. So are they going to want to attract electrons? The metals. No, they want to get rid of them. So they have very low electronegativity. So metals are going to have high electronegativity, and nonmetals will have high electronegativity. Metals will have low electronegativity. Okay? All right. So we'll play Trinity coming up in a few minutes. First ionization energy then. Ionization energy is essentially how much energy it would take to go in and grab an electron and pull it off. Okay, so let's talk about how that would look if I can find a periodic table to talk about. I thought I had saved one on here. Did that not save from last week? I did this last week, you guys. I just can't get anything to stick. But, oh, shoot. That. Copy. Ionization energy. Here we go. Okay, there. Now I got a periodic table I can work with. Okay, now I can write on here. They won't get mad at me. Okay, so first ionization energy. Remember, as we've moved across a period to where we've gotten to here, we've increased our effective nuclear charge, right? We've added protons. So to come in and try to grab an electron off of neon is going to be much harder than trying to grab it off of lithium, because lithium has a lower effective nuclear charge. Okay? If we look at going down the periods here, as we're moving down, let's say we're comparing lithium to francium, francium's outer electron is going to be so much further away from that nucleus that it's going to be easier to grab an electron off of here. So when we look at ionization energy, helium is going to have the highest ionization energy of everything, because it has 2 electrons and it's really close to that nucleus. So it's holding on super tight. Okay, so ionization energy, as you go up the periodic table, because you're getting closer to the nucleus, and as you go across the periodic table, because you're increasing effective nuclear charge, that ionization energy is going to get higher. And ionization energy, like I said, is just how much energy it would take to go in and grab one of those electrons off of an atom and form an ion. That's why it's called ionization energy. Make sense? All right. So that takes us to the end of our trends. I want to talk briefly about photoelectron spectroscopy. It sounds like a really complicated term, but it's not bad. Okay, so you should have some notes in there. The next section is 6.5, I believe. They're called photoelectron spectroscopy. Can you find those? All right. So we talked in chapter 5 about how when light shines on a metal, it can sometimes knock those electrons off. Do you remember that? We talked about that in terms of like solar calculators, solar cells. We talked about how you have to have the right frequency of light with enough energy to be able to pop the, like red light might not do it, but green or purple light might. Do you remember that? Okay. So that's what we're looking at here. We're looking at the energy that it's going to take to get those electrons to come off of there. So we looked at a diagram like this where we said like, oh, the red light isn't powerful enough, but the green would be, and then the violet light would even be more. So you're going to get more energy out of that and get your electrons to move faster. So what they're doing is they're shining this light in, they're causing those electrons to come off, and they're taking information from that and figuring out how tightly bound those electrons are. Okay? And then they're putting it into a graph. So what I want to do is I want to show you how to read these graphs today. Yeah, we're going to talk about it. We'll talk about everything that's going to be due at some point. I just want to flip over one more page. Flip over one more page. There you go. That's where you should be. All right. So when you are looking at these graphs. The problem is sometimes the higher number will be on this side over here, and sometimes the higher number will be on this side. So the first thing you have to do when you get one of these graphs is you have to look at the x-axis and find where the numbers are bigger. The side that the numbers are bigger, you can write down, or you can think about it in your mind, nucleus. Okay? So you can imagine that this is an atom, here is your nucleus, and now we're moving out into these electron levels. Okay? So if we go back to our periodic table, back to chapter 5, when we were doing our electron configuration, where do we always start?
On the inner circle.
Yeah. Where do we start on our periodic table? Chutes and ladders. Yeah, we always started at hydrogen, right? So hydrogen and helium was over here. What is my N value? What block am I in? And how many electrons are there? Well, that's where you have to look at your graph. Okay? So this is going to be 1. This is number of electrons. And they're telling us at the top here that there's 2. So 1s2. And these are your 1s2 electrons because they're going to be closest to the nucleus. And you know that your nucleus is over here because this number is the bigger number on the x-axis. See how that works? So after 1s2 comes 2s, and this is where you have to look at your graph. It's 2s. Well, no.
Oh, 2s1.
See how this one is the height of 2 electrons? This is the height of 1 electron. And sometimes on these graphs, they'll actually have, like over here on your y-axis, they'll have a 1 and a 2 over here. Instead of numbering them on top, they'll be numbered off to the side. So you can see that this would be 2s1. Now they're going to want you to identify what element this is. So what element has the electron configuration of 1s2, 2s1?
Lithium.
Lithium. So that's how you would identify the element.
Oh, it actually says it.
Yeah. All right, so let's look at this guy. Okay, now this one they've had to break down into 2 different graphs because the graph paper wasn't wide enough. Okay, so I'm going to look at, and you can imagine that this graph is just up here, continuing on. But we couldn't fit it on the slide like that, with you still being able to see the numbers and everything. Okay, so where is my nucleus here? Where's my bigger number on the x-axis? Right over here. Okay, so now I'm going to start from my nucleus and I'm going to start labeling the tops of these peaks. So this is going to be my 1s, and I have 2 electrons. Then I drop down with my x-axis, and I keep moving out from my nucleus. This is going to be 2s2. And then following that, after 2s comes 2p. And this is going to be 2p4. So here's my electron configuration. I have to figure out what this is. I find that electron configuration is oxygen. I could add up my electrons too. 2, 4, 6, 8. Oxygen's atomic number is 8. So not too bad.
Yes, not too bad.
I'm gonna go to you.
All right, here is a sample of an unknown element. Without cheating down here and looking at the bottom or looking on your sheet, I think it's already printed on there. See if you can figure out what element this is. I'm going to identify my nucleus. Is it making sense how I'm getting my numbers, where I'm getting this from,
Yes.
how I'm flowing through this?
Yes.
I get the number of electrons, but I don't get like how you're getting the groups.
I'm just following my periodic table. So my sequencing with my periodic table. Okay. So remember we started with hydrogen and helium. That was 1s. And then after hydrogen and helium, we went to lithium, beryllium. So that's my 2s. Then I go to, after beryllium, I go over here to boron. Remember how we did the electron configuration? So that's my 2p.
And the numbers at the bottom match up with the atomic mass.
Don't worry about these numbers.
Okay.
Yeah.
Those numbers are how much energy it's going to take to pull off those electrons.
Oh, so
And as you're moving away from the nucleus, as you're moving away from the nucleus, it's getting easier and easier and easier to pull those electrons away because it's getting further out. Remember?
from right to left, it's easier.
Not necessarily right to left. Okay. Okay, right to left on the graph or on your periodic table?
On the graph.
Okay. So remember, with the graph, these graphs can be set up different ways. So you always have to look for where the number's the biggest, and that's where your nucleus is. Sometimes these graphs are flipped around on their axis. You'll see them reversed sometimes. So you got to be really careful with that. That's why I said the first thing you have to do when you get one of these graphs is look at the x-axis, find the bigger number, and that's your nucleus. And then work your way from the nucleus out to the element that, you know, the electron configuration that you're at the end. Good? So I keep working out until I run out of electrons, and wherever I land, that is the element that I'm at. So this is aluminum. Okay? So here, again, now look at this graph. What has happened to my x-axis? It's flipped. Okay? And I've seen them different ways. So you got to be really, really careful with these. Okay? So this time, this is going to be my nucleus. So I'm going to start there. All right? They didn't give me any numbers on the top up here, but they gave me numbers over here that say number of electrons. So I'm going to start here. Chutes and ladders. We're starting back at hydrogen and helium. So this is my 1s. I have 2 electrons. After 1s comes 2s. I have 2 electrons. Here is my 2p, and this time I have 6 electrons. After 2p comes 3s, and then finally 3p, and that's going to be 6 this time. Why is there such a gap here and between here and here and the energy that it requires to pull those electrons off?
Because there are different groups.
Well, you're going down.
So you're adding,
Rings, orbitals,
which means that you're increasing your
distance.
distance. Right, okay? Now, here, between here and here, you're still in that level 2. It's just this one is just a scunch closer to the nucleus than this guy's. but very, 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 very little different in distance. Okay. Now let's identify what element this is. This is 3p6, so this guy is argon. Okay. Using a different color pen, superimpose the 1s electrons for chlorine and potassium. Okay. So superimpose the 1s. So we're looking at the 1s electrons here. So those are the ones that are right here. I want to look at chlorine. Well, this is chlorine versus argon. So chlorine on my periodic table is here. Argon is right next to it. Okay. Is distance much of a factor here? No. But what is? What is the other part of Coulomb's law? Huh? Number of protons, that effective nuclear charge. So which one has a higher effective nuclear charge, chlorine or argon? Argon, right. So which one's going to hold on to their electrons stronger? Argon. So chlorine is going to be just a little bit easier to pull off than argon. But there's still 2 electrons there. This is the 1s level. So this, my dashed line, is chlorine. I don't have 2 different colors to work with here. Okay. Now, we need to look at potassium. So potassium is down a level and way over here on my periodic table. If I'm using this as a periodic table, right? It's down a level and way over here. Its effective nuclear charge is greater or less than argon? Greater. Is the distance of the 1s electrons, we're still talking about 1s's, okay? We're not talking about way out here, just the 1s. They're about the same distance. So we haven't changed the distance much, but we've increased the effective nuclear charge. So because of that, and I'm going to have to do this kind of a darker red, that's going to be the way I'm going to draw my argon. Okay? It has a higher effective nuclear charge, so it's going to be harder to pull that electron off than argon. Make sense?
Yes.
All right. Now, the next one is using a different pen color, superimpose the valence electrons for chlorine and potassium. So valence electrons are the electrons way out here. How many valence electrons is chlorine going to have? 7. Okay. Argon has 8. Okay. So it's going to be easier to pull off whose? Argons or chlorines?
Argons?
What's the difference between them? It's not distance, it's number of protons. So is it going to be easier to pull off argons or is it going to be easier to pull off chlorines? Chlorines, because it has a lower effective nuclear charge. So chlorine, we still have 3s2. We have 2 of those electrons. And then we're going to have up to 5. Oh, shoot. Why did that? No. Darn. I was doing so good there, you guys. Okay. It's just weird. Just like went away. But I only go up to 5 because chlorine only has 7. 2 plus 5 is 7. All right. Now, let's talk about potassium's valence electrons. How many valence electrons does potassium have? 1. Where is that electron? Oh, this should have been potassium, shouldn't it? Shoot. I can't change that. Should have been potassium. Where is that 1 electron of potassium going to be? Yeah, it's going to be further down this way, and I'm kind of run out of board space here. So you would have to draw it out here, and there would only be one of them. So it would be something like if I wanted to continue my board space, you know, over to here, I would have one electron right there for potassium. Okay. Oh, that's it. All right, so we are at the end of new material for Unit 6, okay? I'm going to hand out to you your periodic table of Craig. I would like to have, I need to kind of call up a calendar here because I think I might switch things up once again to your benefit.